Hello students, in this lecture I am going to tell you about density of states in one dimension. So in previous lecture we have seen in one dimensional potential well, infinite potential well. So we have infinite potential well in one dimension. So the length of, you can say, dimension of this potential well is from 0 to L, and in the we have defined three regions. So first, second and third regions. So in first region the potential v of x is equal to infinite. Here potential v of x is equal to 0, and here potential v of x is equal to again infinite. So for this potential well we have calculated the energy eigenvalues. So energy eigenvalues which are En is equal to n square pi square ml square. So this h cross is nothing but h upon 2 pi, and this L is the, you can say, length of this potential well. So if we see this equation carefully, so we will find, we can say that the energy eigenvalues are dependent on the, you can say, n, basically if the dimension of the potential well is fixed and the mass of the particle inside this potential well is fixed. In that case the energy eigenvalues depends only on n square. That means the state in which that particle is present. So if I want to calculate number of energy states between energy E and E plus dE, so that will be termed as the density of states, or number of energy states in between energy, you can say, E and E plus dE is called as density of state. Because we are calculating it for one dimension, so it will be called as density of states for one dimension. So we will start, in order to calculate that, we will start with the energy eigenvalues of the infinite potential well. So it is given by En is equal to n square pi square h cross square upon twice ml square. Okay. So if I rearrange this term properly, so I will find n square is equal to, so I will keep this n square on the right hand side and twice ml square on the left hand side, divided by this pi square and h cross square. So I will get n square is equal to twice ml square En upon pi square h cross square. Or if I want the value of n, in that case I will take the square root of the right hand side term. So if I so I will take this En is equal to under root twice ml square En upon pi square h cross square, which I can write as, let's say, L upon pi square h cross square. Okay, I will write it separately. So into twice m raised to 1/2 separately, and En, sorry, this En raised to. So if I do that, what I found is L square upon pi square h cross square raised to 1/2. These two terms are constant, and only term which is variable is E, that is energy will change when we change the n. So we differentiate the above equation. So differentiating and multiplying the above equation by 1 by 2, we get a number of quantum states of the electron between the energy E and E plus dE. So what we did, we have multiplied it by 1 by 2 to the above equation. Why? Because we have, let's say, this is, let's say, number line. So we start from the 0. Here we have 1, here 2, like this way, 3, and here we have -1, -2, like this way. So we have ignored these negative parts, and including 0, we have ignored this half part. So only half part of this number line is present. That's why we have multiplied it by 1 by 2 factor. So which is here, I have multiplied here by 1 by 2. So the first term, L square upon pi square h cross square raised to 1/2 gives L upon pi h cross, and second term 2m raised to 1/2, it will be as it is. And with the derivative, only derivative of the variable, only variable that is present here is energy. So if I take the derivative of this energy, it will be 1 by 2 into En raised to -1/2 into dE, because we know that. So let's say I have energy raised to energy raised to 1/2. If I want to find the derivative of this, then it will be 1 by 2 into En So E raised to 1 half minus 1 into dE. Okay, so it will be like this. So if I find the derivative, so it will be like 1 by 2 into E raised to minus 1 by 2 into dE. So if I put this so this term at this point, I will get this equation. So I will just rearrange these terms. So this 2 factor I will multiply here with these 2, and I will get L upon, let's say, pi. Okay, so sometimes it is good practice to combine the twice m upon h cross square raised to 1 half, because this is many a time this term is made separate. So we have just rearranged our equation like this, and this right hand side part as it is. So now what we will do, let us denote the number of quantum states between E and E plus dE by ZE. So if I represent number of quantum states between E and E plus dE by ZE, so we can equate it equal to dN is equal to ZE. So this dE and dE, if we cancel it out, we will get an equation for the number of energy states between E and E plus dE, and that will be L upon 4 pi into 2m upon h cross whole raised to 1 by 2 e raised to En raised to minus 1 by 2. So this will be number of energy states. Okay, but each orbital can accommodate 2 electrons, because let's say we have one orbital, in that spin up and spin down 2 electrons can be accommodated. So if I want to calculate, so this gives me density of orbitals. Okay, but if I want to know how many electrons will be accommodated, so I have to multiply spin up electron and spin down electron. 2 electrons will be present in each orbital. That's why I have to multiply it by 2. So I will get ZE is equal to 2 into L upon 4 pi twice m raised to 1 by 2 En raised to 1 minus 1 half as it is. So I have a factor of 2 in order to consider this spin up and spin down these 2 electrons in that energy states. So finally we get this equation. So this equation, which is represented ZE is equal to L upon 2 pi into twice m upon h cross square raised to 1 half into En raised to minus 1 half. This gives me a density of states in one dimension. That means number of energy levels which can exist between energy E and E plus dE, E to E plus dE. So if I know the energy and a small change in that energy, so in between that energy levels I will have number of energy states which can be determined by this equation. So if you see this equation carefully, you can find it out. L upon 2 pi, so this is the, you can say, dimension of the potential well, twice m upon h cross square raised to 1 half into En raised to minus 1 half. So the only factor on which it is dependent is n. So if the value of n is known, we can calculate the energy eigenvalues, and if we substitute these values in this equation, we can find out number of energy states between E and E plus d. So with this we will stop at this point. Thank you for watching.